you and good afternoon. My name is Perera. I am from University of South Australia. Let me now introduce our work on human detection and motion analysis from a quadrotor UAV. The motivation behind this work is using a UAV, especially in search and rescue missions and situation awareness missions. So we specifically selected hovering quadrotor UAV because of the operational simplicity and the cost, the low cost of the UAV, and especially in for example in surveillance missions as well as in search and rescue missions, the UAV has to recognize the actions of humans and sometimes has to take responsive actions. The difficulty in this research question is the articulated nature of the human body, because there are infinite number of poses the human body can take. And another challenges are when you are recording from a UAV, especially from the aerial point of view, there's a perspective distortion. That means you can see large heads and shoulders and small feet, and sometimes motion blur and wind gust. There are different challenges. And so in this work, we try to estimate the human gait as well as trajectory from a drone. And we used a 3DR solo quadrotor with a GoPro camera. In our experiments, the distance between the camera and the human subject was roughly 30 meters, and we used different heights. So the solution comprises of these 5 modules: a detector and a perspective distortion corrector, and human segmentation, so the image segmentation unit, as well as pulse estimation and trajectory estimation units. So for the detection part, we used the neural network method that is based on RCMN, that is for region-based conventional neural networks, and we created our own data set. For the data, we used some publicly available data sets, namely like Mobiline, Virat, Minitron, UCF area, PETs, as well as our field videos. And we followed the standard artificial intelligence and machine learning approaches when training these images, and we divided into training and testing data sets, and we trained a detector, and we achieved a nearly perfect result in the detector. So detector is only to detect people from the aerial videos. So in the for the detector, behind the detector, we use already trained neural network that is called AlexNet. It is very popular in this area. And yes, these are some results. The first 3 rows correspond to our field videos, and the last 3 rows are from publicly available aerial data sets. And the red color boundary boxes are detected region of interest. And once the person is detected, the next step is to correct the perspective distortion. So for that, we use a perspective correction module. Basically, when you align with, so when you see from an aerial viewpoint, there's a limit that you can correct the images. For example, here we manually create vanishing points. So these are called vanishing points. So when 2 parallel scene lines meet together, it is called a vanishing point. So manually create vanishing point for different heights, and we calculate a matrix called homographic matrix or homogeneous matrix. And we use manually created homogeneous matrices to correct the perspective distortion of each aerial images at different heights. But there are some limitations. We could do it for some extent, but not perfectly. The next part is the segmentation part. This section we still investigate which technique to use for the best segmentation. Currently, we use Gaussian filter as well as silhouette extraction as well as dealing with blobs, image blobs. But it is not still not a perfect solution. We try to do more work on in this area. And the denoising parameters are subjected to improvements. That means from case by case, we have to adjust these parameters. That means from video by video. So this is the core part of this solution. That is called dynamic classifier selection. A normal classifier, the standard classifier, normally it classifies different objects. But this dynamic classifier has a special meaning. That means you select if there are multiple classifiers for some task, you don't need to execute all the classifiers to get the result. So you select few classifiers based on some logic, and you execute only those few classifiers for your task. That means it is computationally less expensive. So here in our solution, we create 64 classifiers. Each classifier contains 4 classes. In standard approach, you train a classifier with 64 classes, but in dynamic classifier approach, you train 64 classifiers, each with 4 classes. And so this is a unique solution we developed. And this technique allows to classify human images robustly. The secret behind this, it's not secret actually, the logic behind this approach is it limits the number of classes for the current state. For example, for this red color window, the prediction states are the window itself as well as these yellow color windows, not any other states. So in this way, you limit your classes. That means there's a high chance of getting the accurate estimation. And for this part, we use a different training data set, and the number of images are 1017. And again, we divide. So we create this data set using 8 poses as well as 8 viewpoints. That makes up to 64 classes. That is viewpoint pose pairs. The next point is a trajectory estimation. Here we create 3D skeletons based on the estimation, based on the classifier output, and then we localize the selected 3D skeleton in a unitless space in a MATLAB environment. And here these images, the bottom left, in the bottom left corner, the first row corresponds to original image sequence, and the second row is the perspective corrected image sequence. You can see it with stretched images, and the third row is the segmented image sequence, and the last row is the skeleton series. And the middle image is a skeleton train. That means in other terms, that's the estimated trajectory. And the bottom right corner image, it corresponds to human foot touching positions. Red color dot corresponds to right leg, blue color to left leg. So this is the final estimated trajectory. These are the estimated poses. And let me show you a small demo. This from a 10-meter height. The height is 10 meters. And this is from a 40-meter height. And again, these are some results. When operating at 10-meter height, we consider this perspective distortion is negligible. Therefore, we don't correct it. So, and you can see in the other other three heights. Okay, the first column is the trajectories. First column correspond to trajectories created from original images without correcting the perspective distortion. And the second column corresponding to perspective corrected images. So you can clearly see the improvements of the trajectory after the correction of the perspective distortion. Yeah. So we try to actually this is an ongoing work. This is the initial work that we've done. We try to develop this work for the next step. That means identifying challenging human action like fighting or maybe asking help or anything. So we are working on that part right now, and we are also investigating the best detection as well as feature extraction method. Currently, we have experimented with CNN features. Here we use Hawk features, histogram-oriented gradient features, because we use this one. It is computationally less intensive. It is easy to implement on board on a drone. And we have already tested with CNN, but the CNN results was not good as Hawk. Therefore, yeah, we are still working on that area as well. And for the future work, we try to improve. We try to run this algorithm on board as well as develop this further for challenging situational environment missions and search and rescue missions.
Thank you very much for a very interesting presentation. Okay, we take questions from the floor. Okay.
What's the minimum pixels which the system can predict that he is a human?
Right. Okay. For this experiment, we used HD images, that is 1980 and 1200 or something, that the non-standard HD image. That is one challenge in this kind of research, because when the quality of images are low, qualities are low, then it is very difficult to predict what is the exact pose of the human body. So when it is blurred or less resolution, this solution will not work. So you need highest images, not I mean not 4K, but in the standard resolution limit. Yeah.
No, I have a question. What's the software that you use to develop this thing?
We basically use MATLAB, as well as we work on Python scripts to implement it on board. And yeah, and some to speed up the computations, we use Python, and for the graphical representation as well as for like these graphs and the skeletons, all those kind of things we use MATLAB. But for speedy computation, we use Python.
You use onboard computer, what kind of TX1 something?
Actually, we are working on, we are already testing on Android XU.
Android, even Android is enough.
Actually, yeah, our experiments show it is possible, as well as we are now trying to use Intel neural sticks.
TX1 is NVIDIA computer.
Not NVIDIA, not Jetson one. There's a small USB size stick, neural computing stick from Intel. That's the other mobile device that we are trying to integrate.
Okay. Why not the Jetson?
Yeah, Jetson is a good thing. Actually, we are still thinking of the money.
Oh, the cost.
It's costly.
Okay. Another question. You do the learning offline, right? Of course.
Yes, it's learning offline.
Okay. So the implementation is on board, but learning is offline.
Yes, because when we deploy the trained model, so first we have to train whatever the model like that via or detector whatever.
Yes.
With the labeled data offline. Then you deploy that in onboard computer.
Because sometimes you know the YOLO, you only
Yes, YOLO. Yeah.
YOLO. So
Yeah. YOLO is a detector. It is the YOLO is trained. YOLO is a very popular detector like RCMM.
Yeah.
It is trained on ImageNet on 1,000 classes. But actually here what we do is we used another neural network like AlexNet. It is similar to YOLO, but YOLO is a detector. It's not a trained neural network that is facilitate transfer learning.
But you cannot use part of it or something.
Yes, we
cannot
can
utilize.
use, but there are some limitations in YOLO because YOLO is good for real-time object detection on given classes. But here we are interested in humans. So YOLO is a general purpose detector.
Any other questions? Okay. Thank you very much, Mr. Perera. Thank you very much. In that, I think we have concluded our presentation for today. So thanks for bearing with us until the end of the session. So I hope we will see you again tomorrow for the tomorrow session and the closing ceremony. Thank you. Assalamualaikum warahmatullahi wabarakatuh, and a very good evening.